Welcome back. Today we're driving deep into, well, history's raw power, really. We're looking at the Carrington event.
Yes, the most intense solar storm ever recorded, hitting us back in September 1859.
So, just what was the Carrington event in simple terms?
Okay, so imagine a massive explosion on the sun, a coronal mass ejection, or CME. This huge cloud of charged particles slams into Earth's magnetic shield, the magnetosphere.
And the Carrington one was just huge.
Exceptionally so. It caused what we call a severe geomagnetic storm. Back then, the tech was simple. Today, an event like that could cause potentially catastrophic electrical grid failures, widespread blackouts.
That's chilling. So our mission today is to unpack that historical drama from 1859 and see, how relevant it still is for us now.
Absolutely. It's a critical case study.
Okay, let's start at the beginning, the observation itself.
Right. September 1st, 1859, you have two British astronomers, Richard Carrington and Richard Hodgson, working independently.
And they both saw it.
Yes, pretty much simultaneously. They observed this incredibly bright flash and eruption on the sun's surface. It was actually the first time anyone had ever recorded a solar flare.
The first time.
Yeah.
And then things happened fast.
Incredibly fast. The CME, the particle cloud from that flare, traveled the 93 million miles to Earth in just 17.6 hours.
Which is unusual, right? Don't they normally take longer?
Much longer. Usually it's several days. This speed is really a key part of why the storm was so intense.
Why was it so fast?
Well, the leading theory is pretty interesting. It seems another smaller CME had erupted a few days prior.
Okay.
And that first one might have essentially cleared the way. It swept aside the slower solar wind particles that usually fill the space between the sun and Earth.
Ah, so it created a kind of express lane for the big one.
Exactly. Less resistance, much higher impact speed. It suggests, that timing and the sequence of events can really amplify the effects.
Okay, so this super fast CME hits Earth. What did people actually see?
Visually, it was spectacular. Auroras, the northern and southern lights, were seen globally, and I mean globally.
Not just near the poles.
Not at all. They were reported as far south as south-central Mexico, Cuba, Hawaii, Colombia, places that never see auroras.
Wow. And there's that famous story, isn't there, about the miners?
Oh, yes. Over the Rocky Mountains, the aurora was reportedly so bright that gold miners woke up in the middle of the night.
Thinking it was gone.
Thinking it was dawn. They actually started making breakfast, and in the northeastern U.S., people could apparently read newspapers just by the light of the aurora.
That's just incredible, pure spectacle. But it wasn't just the light show.
No, not at all. While the sky was beautiful, the infrastructure of the time started failing pretty dramatically.
Telegraph systems.
Precisely. These geomagnetically induced currents, GICs, started surging through the telegraph lines across Europe and North America.
GICs. So currents induced in the ground by the storm.
That's right. The storm makes the Earth's magnetic field wobble, and that induces powerful low-frequency currents in long conductors, like telegraph wires.
And the effect was immediate.
Oh, yeah. Systems failed everywhere. Operators reported getting electric shocks. Some telegraph pylons were actually seen throwing sparks.
Sparks? And then there's that Boston to Portland story.
That's probably the most famous technical anecdote. The operators on that line disconnected their batteries, and they were able to keep sending and receiving messages for about 2 hours, powered only by the current induced by the aurora itself.
Just running on space weather. Amazing.
It really was.
Yeah.
Direct proof of that solar-terrestrial electrical connection.
Okay, so that was 1859. Let's pivot to now. What's the so what for our modern, much more complex world?
Well, that's the crucial question. If a Carrington-level storm hit us today, the impact on the electrical power grid could be devastating, far beyond telegraphs.
We're talking about potential grid collapse.
Widespread, long-duration blackouts are a real possibility. Think about everything that depends on electricity. Heating, cooling, communication, water supply, finance.
The costs must be astronomical.
Some research back in 2013 tried to estimate it. For the U.S. alone, the figures ranged from $600 billion up to maybe $2.6 trillion.
Trillion. With a T. That's sobering.
And it's not just a theoretical threat. We had a very close call relatively recently.
You mean the 2012 event?
Exactly. July 23rd, 2012. A solar superstorm, definitely Carrington class in its power, erupted from the sun.
But it missed us.
Just. Its trajectory didn't intersect with Earth's orbit. It missed us by about 9 days' worth of our orbital path, a very narrow escape.
So we dodged a multi-trillion-dollar bullet just over a decade ago.
Pretty much, yes.
So Carrington is the benchmark from recorded history. But is it the biggest storm possible?
That's where things get even more interesting. We have ways to look further back beyond written records using things like ice cores and tree rings.
And do tree rings tell us about solar storms?
Yeah. They look for specific isotopes, particularly carbon-14. You see, massive solar storms bombard the upper atmosphere, creating an excess of certain isotopes like carbon-14.
And the trees absorb this carbon-14.
Right. As they grow each year, they incorporate the atmospheric carbon into their rings. So a big spike in carbon-14 in a particular tree ring points to a major solar event around that year. These are sometimes called Miyake events.
And have we found evidence of storms bigger than Carrington?
Oh, yes. There's very strong evidence for exceptionally large events, particularly around 774, 775 CE, and again around 993, 994 CE.
Bigger than Carrington? How much bigger?
Well, estimates vary, but the data for the 774, 775 event suggests it might have been, well, perhaps 10 times stronger than the Carrington event, maybe even more.
10 times or more.
Yes. Which really leaves us with a final thought for you, the listener, to consider.
Go on.
While 1859 set the benchmark for what we've experienced in modern times, the deep historical record, written in trees and ice, suggests the sun is capable of far, far greater fury.
So, the Carrington event, the big one we study, might actually be relatively minor compared to the sun's maximum potential.
It certainly raises that possibility. And it forces us to ask, are we truly prepared not just for another Carrington, but for something potentially much, much larger, something from the deeper history of our planet's interaction with its star?